In this video, we want to connect the Gibbs energy of reaction, which occurs during a cycle of an electrochemical cell, with the electromotive force that is produced by that cell. So we're going to connect delta G and E. So to start off, let's think about the total charge which is traveling through this electrochemical cell during any given period of time. So we'll have our total charge, which we'll denote by Q. So Q, that's going to be equal to N, which indicates the number of moles of electrons that travel for every stoichiometric equivalent in our reaction. So for our tin and nickel case, this N would be 2 because there were 2 electrons for every for every reaction of every tin and nickel ion and solid. So that'd be N times Avogadro's number goes from number of moles to actual number of electrons. And then so we have the number of electrons here, multiplying that times the charge of the electron QE gives us the total charge which passes through during the course of the reaction. Okay, so to help us out here, we're going to define a new constant, which we're going to call Faraday's constant. And Faraday's constant is equal to the number of coulombs so the total charge, the number of coulombs in a mole of electrons. So it indicates total charge of 1 mole of electrons. So Faraday's constant, which I'm writing in this kind of script cursive F here, is equal to, it's going to be Avogadro's number times the charge on an individual electron, which is going to be 6.022 times 10 to the 23rd per mole times 1.90 times 10 to the minus 19th coulombs per electron. So F is going to end up being equal to 96,485 coulombs per mole. And this will be a pretty central constant throughout this series on electrochemistry. Okay, so that's our Faraday constant. So that gives us that the total charge is going to be equal to the number of moles times our Faraday constant. So now our total charge is going to equal Faraday's constant times N, the stoichiometric number of electrons which occur during the reaction. All right, so how much work is getting done, or how much work can be done by these electrons traveling through this voltage? Well, voltage is just in units of joules per coulomb. So if we multiply joules per coulomb times coulombs, then we get joules. So the amount of work that's done by an electron traveling through an electric field, or any charged particle traveling through an electric field, that amount of work is equal to the charge times the change in potential. So that is equal to, as we've seen here, the charge is going to be Faraday's constant times N, and the electric potential, delta V, is going to equal our EMF, E, our electromotive force, which we defined in the previous video. So the total work that gets done is equal to NFE. All right, so how does this connect to our Gibbs energy of reaction that we want to connect it to? Well, delta G, as we derived way back on the series on Gibbs and Helmholtz energy, that's equal to the negative amount of the maximum possible work, which is not mechanical work, so non-pressure volume work. The negative of that is equal to the maximum amount of non-pressure volume work that we can get out of a system is equal to the negative Gibbs energy. So this is our electrical work that we can do in the system. That's non-mechanical work. So the change in Gibbs energy during the reaction is just equal to minus this quantity here. So what we have is that our delta G of reaction for an electrochemical cell is equal to minus N F E. And this result is the Nernst equation, and that's probably the central equation of electrochemistry because it relates something that we measure here via the flow of electrons in the electromotive force, the change in potential, and it connects it to the quantity which we're familiar with for chemical thermodynamics, which is our change in Gibbs energy of the reaction. All right, so we know our delta G of reaction is correlated to this value. So how does this work relative to standard Gibbs energy of reaction and equilibrium constants and all those sorts of good things that we're also used to? All right, so let's say we have some typical reaction like we used in the equilibrium playlist, where all the nus are stoichiometric coefficients and all the capital letters are chemical species. So we have our reactants A and B, we have our products C and D. Each of them has a stoichiometric coefficient, nu A, nu B, nu C, nu D. Okay, so for a given, for our equilibrium, if we're interested in the Gibbs energy of reaction, so delta Rg would be equal to the standard Gibbs energy of reaction plus RT log, and then our reaction quotient Q, which in this case would be the activity of the products raised to their stoichiometric coefficients. Remember, activity is kind of like a metric of concentration, but more directly related to the Gibbs energy. At very dilute concentrations, activity and concentration are the same. So we have activity of the products to their stoichiometric coefficients divided by activity of the reactants to their stoichiometric coefficients. So that's our Gibbs energy, but we know that that's equal to minus NF E. So now we can relate that to our E of our cell, defining this quantity here again to be Q, our reaction quotient. So what we have here is we have the EMF of our cell is equal to, and just like we have a standard Gibbs energy, we're going to have a standard EMF minus gas constant times temperature divided by number of moles of electrons divided by Faraday's constant. Let me make that a little bit better. Over NF times natural log of Q. All right, so we're going to have some quantities in here that we need to define. So we have E naught, which is the standard EMF of the cell. So we're going to look more into how we find the standard EMF, just like we can find a standard Gibbs energy of reaction from some values in tables. There will be some values in tables which help us get at this value here. And then the specific conditions are given by the reaction quotient and what our N is for our given cell. All right, and E naught of cell is also equal to, it's equal to the EMF of the cell when the activity of all species in the cell is equal to 1. So for example, when all things are at 1 molar of concentration or 1 molar of activity, when all gases are at 1 bar of pressure or 1 bar of fugacity, etc., etc. So we have our final results here that we have our EMF is related to a standard EMF minus RT over NF log Q, relating that to our Gibbs energy. And then our standard EMF as well is going to relate to our standard Gibbs energy because our E naught is relating to the equilibrium constant via RT over NF times the natural log of K. Because whenever Q equals K, then we have that we're consistent with our standard EMF there, just like when all of our activities here are equal to the equilibrium constant, then we're at equilibrium, and delta G is equal to minus RT ln K. So delta G being equal to minus RT ln K, our EMF, our standard EMF is E naught is equal to RT over NF ln K.